Okay, today we're going to talk about water vapor, moisture in the air. So we've gone through pressure, we've gone through temperatures, energy coming in. Well, now we get to move on into water vapor. I thought I would just begin literally by looking at water vapor in the atmosphere. This is a map of it. Mid-level, picked up by satellite. Guess what? Water vapor does have a particularly infrared channel that you can look at to see it. We're looking about 15,000 to 20,000 feet up in the atmosphere right now. The closer to green it is, the more water vapor is available. And blue, of course, would be some water vapor, but then when you get down to the yellows and all, there's less and less. So, looking at this, here you have out in the Pacific, and there's lots of water vapor. You would expect that coming across the Pacific into the Pacific Northwest and parts of Canada here. And it flows on eastward. And you'll notice if you're a little bit more relative humidity, more water vapor in this area here. Up here, the remnants of Fiona, lots of water vapor around it right now. There's another plume of moisture coming up here. And remember, this is at 15, 20,000 feet up. But here is Ian down in here, just getting going. Look at all the moisture around it. So you can see, by looking at this, we can see where water vapor is moving. We can look at it and see where there's more of it. And when you see where it's coming from, sometimes you get a better idea of just how much precipitation might be going to fall in your area. And I haven't had any hardly for recently. About 4 weeks now, I have hardly had a drop of rain. And unfortunately, I'm trying to grow grass, so I've been watering like crazy to try to get it to grow. But another way to look at water vapor, of course, would be to look at a surface weather map. And here we're going to look at dew points. So if I look at a dew point now, here's what's left of Fiona up here, clobbered Canada. Dew points, lower left hand of a station symbol. Look at that, 35-degree dew point, 30-degree dew point. They are relatively dry air. Here's a 19-degree dew point in the desert out here by Las Vegas. 23, very dry air. Now, let's look down towards some moisture we saw coming up through the Gulf of Mexico and stuff. 80-degree dew point, another 80. So there's lots of moisture down here. And the difference between the temperature and the dew point is really going to influence how close to saturation the surface air is. The further apart, the drier the air actually is in relative to saturation, which means there's probably going to be less clouds. Winds move moisture around, as we just saw. And here you can see the winds out of the northwest pulling in drier and drier air. Here you have the winds coming up from the south, coming off the Gulf of Mexico, pulling in moisture. So there's more moisture beginning to come back into that area. So let's explore this a little bit here. So we're going to start this, and we'll move along here. We don't know basically the cycling of the water in the Earth's atmospheric system. And it makes us habitable. We need water to live. So your book talks about atmospheric rivers. I actually showed you one. It was in the Pacific Northwest. If you went out further west, you would find that river going a lot way across the Pacific. Notice these right here. This one was a classic example. All the way across from the southern Pacific, south way over here to over into the United States. And atmospheric rivers can develop on the eastern part of the United States, into the Gulf of Mexico. It doesn't matter where. And land makes a big difference on how that atmospheric river responds. When it's lifted, it's going to dump precipitation. When it's coming down a mountain, be less precipitation. And I went out west this summer. As I was coming out of Yosemite, we were going up over the Sierra Nevadas to come out of Yosemite towards the Lake Tahoe area and heading into Nevada. As we went up, there was some moisture coming in from the ocean, started to precip on us. We had some clouds. We actually had a little bit of snow up in the top of the mountain that day. But coming down, it was wild because you could just see the clouds just disappear. And we dropped into New Mexico with no clouds whatsoever. And every once in a while, eventually, some of the precip did make it across the mountain to us, but not much. Most of it was held up into the mountain. So you can see the influence mountains do have on you. The amount of water, not very much in the atmosphere, really. All of it's confined to the troposphere. And if you dumped it all out, you get about an extra inch over the whole world. Not a lot of water there. So let's look at the water cycle. What happens? Well, oceans, there's lots of water over the oceans, seas. It evaporates water. Some of it, the sun's heating on it. There's evaporation. So that air goes up, warmed by that sun, moves somewhere, and condenses. Makes precipitation. Some of that precipitation is back over the ocean or the lake or whatever. So it's replenishing the water supply. However, some of it might hit the mountains, making snow up on top of the mountain or others. And that could cause some precipitation to run off. I know, for example, in West Virginia, I worked there for a number of years. I had relatives living there. Well, my wife's from there. And when you get the rainfall on the slopes there, it all runs down very quickly into the valleys, into the lowlands. And it causes a lot of potential flooding or flash flooding there because of that. Because the slope of the ground is such, and the ground's made up of such, that a lot of that precipitation is going to come down quickly. Now, humans, believe it or not, have influences on the amount of water in the air. There's an example. They did a study in Oklahoma. What they did was they studied the winter wheat crop, and they looked at the moisture available with it. Plants have what they call transpiration. They upload moisture back into the air even after they've used it out of the ground. Winter wheat does that. And when the winter wheat was not harvested, dew points, a measure of moisture, were running in the 60s in the western part of Oklahoma, where this winter wheat crop was huge. Once they harvested it, we don't have any winter wheat. We weren't getting it out of the ground anymore, the moisture. So dew points went back down into the 40s. It was almost a 20-degree drop in dew point just because of harvesting plants. Yes, we need to harvest the plants. But it's interesting how they influence the amount of moisture in the air. Now, some of this moisture is also going to go infiltration through the ground, go into groundwater storage. And if you're out where you've had a fire, like in the Rocky Mountains and all where they've had a lot of fires lately, that creates a layer that actually doesn't allow any moisture to sink into it. What it does, though, is run off very quickly. That's why they hit areas that have had major forest fires and worry about flash flooding if there's any precipitation there. We learned all about these phase changes with water. We have evaporation, where the molecules, water vapor, enters the atmosphere as vapor. We have condensation. Transpiration is just water taken in by the roots, escapes into the air. Evapotranspiration is evaporation and transpiration. Sublimation, deposition, and precipitation, all methods which water is changing around. So humidity just describes the amount of water vapor in the air. It's going to vary from day to day, time of day. And yes, summer is going to be much more humid than the wintertime. So how do meteorologists measure humidity? Well, we have vapor pressure, mixing ratio, specific humidity, absolute humidity, relative humidity, dew point, precipitable water. Okay, did I give you enough? So we have a lot of choices. Vapor pressure. We've dealt with air pressure all along. So let's just start to the fundamental. The amount of water vapor in the air can be measured as a vapor pressure. And no more than 4% of the atmosphere in the lowest, very lowest kilometer, it might be made up of this water vapor. Typically, it's a lot less. But the higher the water vapor pressure is, the more water vapor is in the air. Mixing ratio. All that is the mass of water vapor, and you pull out that from, say, a 1 meter by 1 meter group of air, and measure the mass of what's left, and you just divide that into the mass of water vapor, and you wind up with grams per kilogram. The larger the number, the more saturated the air is. Specific humidity, we keep the moisture. That's the only difference. Why? There's a reason for it, but you don't need to worry about it. Absolute humidity is the mass of water vapor per volume of humid air. So everything we just talked about was terms when they're saturated. Let's learn what saturation is. Saturation basically means that the molecules are coming into the air and water vapor molecules are changing to a liquid as fast as that liquid is changing back to a vapor. They reach a steady state. When they're the same, that is saturation, when they're equal to each other. In other words, so many molecules are transitioning into a vapor, from a vapor to a liquid, and so many are transitioning back into a vapor. Here you see various vapor pressures. Notice, the hotter it gets, the bigger the vapor pressure. Why is that? Well, molecules move faster the hotter they are, right? So, if a water vapor molecule is very hot, it's vibrating like crazy. It is going to be hard as heck to get that molecule to saturate. So, the hotter the air, the more water vapor it can hold. The cooler the air, slower the less. And oh yeah, ice. Ice is a solid. That means the molecules aren't moving as much. So they actually have a different vapor pressure than the liquid. So that will become important next chapter. Relative humidity we use all the time. You like to know whether, what's the relative humidity today? Is it 100%? And it varies from time to time of day. It's just the vapor pressure over saturation vapor pressure, or any of the other ones, and multiply it by 100. 100% means it's totally saturated. 50%, partway there. And relative humidity can increase by more and more water vapor entering the air, or you cool the temperature. One or the other, or both combined to change the relative humidity. And here, look at the day. Ever think about it? You have fog in the morning. Well, why is that? Well, because the air is coldest. Can't hold as much water vapor. So you're going to wind up getting the highest relative humidity in the morning. As the sun comes out, fog burns off, temperatures are going up, the relative humidity is going to come down. Even though you have the same amount of moisture in the air, the relative humidity is coming down. And by afternoon, it's going to reach its lowest. Then in the evening, it's going to begin the other process. Dew points. We see them on every weather map. It's a way of looking at temperature, what the temperature must cool to if nothing changes to reach saturation. In other words, if I don't change the pressure, this is what it's got to cool to get dew on the ground or to get frost. And you can see how they change from winter to summer. Look how much lower they are in the winter compared to the summertime. So, and as the relative humidity nears 100%, you wind up with clouds. So, now we're going to move into another section that you're going to need to know, but it's not necessarily, I've always found it a little difficult for you all to learn. Think about a parcel of air. I don't care what size. Think of it in your own mind. It can be 500 feet by 500 feet. It can be a mile by a mile. Square, vertical, cube. All right. That parcel of air has one temperature and one amount of relative humidity. The air around it may have a slightly different temperature. Probably does. So as I lift that parcel of air up, maybe a mountain, maybe a cold front or a warm front, the air begins to cool. That parcel of air begins to cool. The air around it is also cooling, but it might be cooling at a different rate. So as that parcel of air goes up maybe 1,000 feet, how did it change in relation to temperatures of it versus the air around it? If the temperature of that parcel of air is warmer than the air around it, it's going to want to keep rising because those push those molecules apart further. It's less dense. It's going to want to keep going up. However, if it's colder than the air around it, it's going to want to sink back down. So that is all we're talking about in stability. That parcel of air is whatever you want it to be compared to the air around it. So if you have air parcels warming, going up, that are not cooling as fast as the atmosphere around it, they're going to tend to be unstable, and they're going to want to keep rising. Unstable air is what you have in thunderstorms, and you can have it during rain events, just regular wintertime storms, during a hurricane. These are when the air tends to accelerate upward. And yes, that air parcel is accelerating upward when it's warmer than its surrounding. It is not just moving at a constant rate. It is actually accelerating. So, if an air temperature is dropping more rapidly than the dry adiabatic lapse rate, and that is a tough thing to find, then it's absolutely unstable. But here's the key. This is what happens mostly in the atmosphere. Conditional instability. Remember that an air parcel is cooling 9.8 degrees Celsius per 1,000 meters when it's dry. Immediately when it gets wet, instead of cooling at that rate, it's only cooling at 6 degrees. So, say the environmental temperature is cooling at 8 degrees Celsius. When the air parcel is being pushed up when it's dry, it's stable. But once it hits saturation, that air parcel is only cooling at 6 degrees. It's going to be warmer than that 8 degrees that's going on around it. That means it becomes unstable. That's conditional instability. And you can see it where the sun heats the air. You get the cumulus clouds. You can see it with fronts. Mountains can do that. They can bring it up. And then there's a level of condensation, lifting condensation level where the beginning of clouds form, where they've lifted up to the point where they get moist enough. You know, we've talked about mountains, lifting processes of mountains. There are lifting processes in West Virginia, on the mountains there, for example. When I used to work in Charleston, West Virginia, if you have an east wind, Beckley, just to the west of Beckley, gets significantly less precipitation than over towards Greenbrier. Convergence winds. So this is what I wanted to hit on today. Hope you got something out of it. Let me know if you have any questions.